In this lecture, we shall be talking about something called algorithmic state machines or ASM charts, which you sometimes call, which is a very useful tool for designing sequential circuits, particularly complex circuits. So, the lecture title is Algorithmic State Machine or ASM chart. Let us see what an ASM chart is. This ASM chart is some kind of a tool, you can say. It is a pictorial tool, just like a flow chart or a state transition diagram that we use to represent finite state machines, something similar, but it captures a lot of information with respect to the FSM. We will see. This is quite useful for specifying detailed logic for sequential circuits, which as said is somewhat similar to flow charts. Now, it specifies two things together. It specifies sequence of events that is reflected in a sequential circuit behavior. Also, it reflects timing relationship between the various states of the finite state machine. Now, in a finite state machine, you recall there are two kinds of pictorial elements. One we represent by circles the states, and the transition represented by arrows. Now, along the transition we specify the inputs and the expected outputs. Okay. Now, in an ASM chart there are three kinds of elements which are shown. We shall see these things: state box, decision box and conditional box. Let us see the function of these. First, the state box. State box is a rectangular box, as is shown in these examples here, which represents the state of a machine. Well, if you think of an FSM, a finite state machine, where you represent states like this, let us say S1, S2 and so on, and arrows indicating transition from one state to another. So, each of these states is represented in ASM by a state box. Now, in this state box you have a state name, either you show the state name inside with a slash, like you can write S1 slash. In the output, optionally you can mention the output lists, or the name you can also show outside the box on the left. There are several conventions, you can use any one of them. And inside the state box you can also contain some register operations to initialize the values of registers. Like here you can have some register operations optionally, and each of these state boxes can have some state assignment. Like you see, when you specify a finite state machine, you only mention the states S1, S2, S3 and so on, but you think that when you synthesize a machine, when you are in the process of implementing it in hardware, you also carry out some state assignment. Like you may say that this state S1 will be using this code 00. So, in the state box, the state assignment is also specified typically in the upper right corner of the box. This we are calling as something called state code. Well, we will take some example to show how the state boxes are created, but this is how, or these are the information it contains, and there can be an optional output list also. Then comes the decision box, just like a conditional box in a flow chart, where if it is true you go here, if it is false it comes here. It is a diamond shaped box, but it can be more general. So, when instead of 2 outcomes there can be multiple output nodes depending on how many possible conditions can be there. So, in the simplest case it can be a binary decision as is shown in this diagram, yes or no, or 1 or 0, right. And conditional box is the last one. It is an oval shaped box which contains some output list. Like suppose I create an oval shaped box, I mention Z1, Z2. It means that these two outputs Z1 and Z2 must be set to 1. And this input arc for the conditional input list must be coming from a decision box, maybe from the decision box it will be coming, right. These are the constraints. Let us look at a somewhat complete kind of an ASM block, that how it looks like. This is an ASM block. First thing is that what is an ASM block? ASM block is something that corresponds to one state of the corresponding finite state machine. So, every state of the FSM, let us say there was a state S1, it was going to some state S2, going to some state S3, maybe there was a self loop depending on input combinations. So, every state will be mapped to an ASM block. ASM block is a structure which will be consisting of one state box corresponding to that state. In this diagram, that state box is shown here. So, you see here this state name is given as S1 with an optional output list Z1, Z2. It says that these are the output list of the state box. Now, this you may give, may not give, this is optional. Now, inside the state box there can be decision boxes and conditional boxes connected to its so called exit path. There can be more than one exit path as is shown here. There can be n exit paths in general, 1, 2, 3 up to n. An ASM block will have exactly one entry path or entrance path, but it can have multiple exit paths. Now, inside it what kind of things you can have? You can have a decision box like this, like you check x1, if x1 is 0, false, you come here, if x1 is true, you come here, which means if x1 is false, you set z3, z4 to 1, then check x2, if it is 0, you follow this exit path, if it is 1, follow this exit path. Then along this path you can check the condition x3, if it is 0, you set z5 to 1 and exit through 3, if it is 1, you continue with something else. Okay. This is how generally an ASM block looks like. So, let us explain this, that same example. So, when the system enters the state S1 from the entrance path, first we have mentioned the two outputs Z1 and Z2 here, means the outputs Z1 and Z2 are immediately set to 1. Then condition x1 is checked. If x1 is 0, which means this path, Z3 and Z4 they are also set to 1. But if x1 is, both x1 and x3 are 0, like say both x1 is 1, they should be 1 actually, x1 is 1 and x3 is 0, you follow this path, then Z5 becomes 1 and the system exits. Okay. Now, there are some rules you need to follow when you are creating an ASM chart. You should remember this. For the same system specification, you can have multiple possible ASM charts. You can draw it in several different ways, but certain rules must be followed. Like the first one says that for every valid combination of input variables, like let's take an example. There are 3 input variables x1, x2, x3. Let us say x1 is 0, x2 is 1, and x3 is also 1, 0, 1, 1. For every combination, there must be exactly one exit path. That means, in that ASM block, for the 0, 1, 1 combination, you must be following the same exit path. There should not be multiple exit paths. And inside a ASM block, internal feedbacks are not allowed. It should be only from top to bottom kind of transitions. Parallel paths to the same exit paths are allowed. There can be multiple paths going to the same exit path. More than one parallel path can be active at the same time. This can be active, this can also be active. Such things are allowed. And as I have showed in the previous diagram, there can be multiple exit paths. So, such rules should be followed when you are drawing or creating an ASM chart. Let us take a small example. So, here we shall show how an FSM can be converted into an equivalent ASM chart. So, we start with a simple FSM description of a sequence detector example. A sequence detector which detects a sequence 101 in the input sequence. Just look at this state diagram. This is the starting state, the top one. So, if the input is 1, you move to this state. So, if the input is again 0, you move to this state, and if you get a third one, you move back to this state with the output 1. That means, you have found out this sequence. Now, this third one means there can be an overlapping sequence also like this. The third one means you have detected a 101 here, but it can be the start of the next 101. So, you move back to this state. So, there can be another 0, another 1. So, this second sequence can be detected again, right. So, from here if it is 0, that means you have to start from the beginning, you go back here, right. Now, let us see. Here means you are trying to detect this sequence 101. So, you have an FSM where I am assuming there is a single output Z and a single input X. This X denotes the serial bit stream and Z is the final output 0 or 1, right. So, the output will be 1 only when 1, 0 and 1 is detected, right. There are 3 states in this FSM. This will correspond to 3 ASM blocks, okay. And let us also make the state assignments. Let us say this state is S0, this is our S1, this is our S2. Let us make the state assignment also 0, 0, 0, 1 and 1, 1, let us say. Okay. So, let us show how the ASM chart may be constructed from this FSM. So, here some of the symbols are not visible, I shall show them. Let us again talk about the 3 states. This is S0, this is S1 and this is S2. So, one by one let us see. This is the ASM block corresponding to state S0. This is state S0. So, this state encoding is also shown here 0, 0. So, the output list is default, it just shows the state name as 0. So, you look at the state as 0, what it does, if the input is 0, it remains in S0, and if the input is 1, it goes to S1. In both cases, the output is 0. So, you see if x is 0 left side, you set z equal to 0 because output is 0, and you go back to the same state, you remain in S0. But if it is 1, then also z is 0, and you go to this transition, you go to S1, you move to S1, right. This is your state S0. So, exactly similar to here. Now, let us look about state S1. This is your state S1. Your state encoding is shown here 0 1. The state name is mentioned. Now, in this state S1, if it is 0, it goes to S2. If it is 1, it remains in S1. So, let us see. So, if x is 0, then you set output to 0 and you move to state S2. But if it is 1, then also output is 0 and you remain in the same state, remain in state S1. So, exactly from the FSM you are mapping here. Now, the last state S2, this is your S2 and this is the state encoding 1 1. Now, in S2 this is your S2, if it is 0 you go to S1, you go to S0, if it is 1 you go to S1 and here the output is set to 1. Let us see what you have done. If input is 0, you go to Z0 and you move to here state S0, but if the input is 1, you set Z equal to 1 and you move here to state S1. So, you see exactly from the FSM you can have a one-to-one mapping to the corresponding ASM chart. Now, you may ask that why do you need this ASM chart? The FSM was good enough, right? But you see this ASM chart is one step forward towards implementing the hardware circuit, implementing the circuit, because you have also done the state assignment. Normally from the ASM chart you can directly design the hardware circuit. So, each state box will correspond to a flip flop and after that some gates you can add, you can directly implement. So, it is really easy to map it to hardware. That is why sometimes from the FSM you create the ASM chart, from the ASM chart you can create the hardware. Okay. So, in this lecture we have given you a very brief introduction to ASM chart. As it said, ASM chart is useful for the complete description of our system, which is more powerful than FSM, because it can also capture the state encoding, and particularly for more complex system, for larger FSMs, this ASM chart is sometimes considered to be an useful tool. So, if you are a system designer, if you are using these tools for designing complex systems, well, FSM is of course one way, and you have already seen earlier, starting from an FSM how you can formally synthesize a sequential circuit. But ASM is another route. Just using ASM also you can generate a hardware. Of course, your hardware may not be that efficient, but for more complex systems it is a fairly simple approach to do that. Okay. So, we have discussed means almost all the different aspects that you wanted to discuss regarding digital circuit design and synthesis, particularly at the gate level and the flip flop level. We talked about synchronous circuits, we also talked about asynchronous circuits. Now, in the next few lectures, we shall be discussing on something which is slightly different. Like once you design the circuits, once you fabricate the circuits in the form of chips, there can be some errors in design, there can be some defects which can occur during the implementation. So, we need to test our circuits. How to test? What are the different ways of testing? These are a few things we shall be discussing during the next set of lectures. Thank you.